1b is a little bit different. So this one has the 3 to the n in the bottom, so this is not a p-series. But I can compare it to a geometric series. The 1 over 3n, that is geometric. That is 1/3 raised to the n power. So we're going to compare to this series, 1 over 3 to the n, which is the same, if you need to write it this way, as 1/3 to the n. Right? I cannot use geometric series for this. It looks really close, but it's not geometric because of the +2. But when I do the comparison, I'm going to be able to use geometric for that. So remember, geometric series are all about the ratio. So in this case, the absolute value of r is going to be the 1/3, and 1/3 is less than 1. So that means this series converges by the geometric series test. Now I want to take that knowledge and ask myself, is this original series always less than this series? Now I will say that the first few terms, it really doesn't matter. The idea is it going to be less than as we go to infinity, right? This is an infinite series. So the 1 over 3 to the n plus 2, is that less than or greater than this series? Same thing. Those are the exact same piece, so it doesn't really matter how you write it. Well, because this denominator is always going to be bigger, it doesn't matter what number you plug in, it's always going to be less than. So does that help me? And because this converged, less than converging is still converging. Less than finite is still finite. So now I can answer this question. So since this converges, right, for all n, and we're less than for all n, now I can make that statement. So because of this information right here, the original series, and you do have to write it out. You can't just say the series because I don't know which one you're talking about. I don't know if you're talking about this one or this one. So the original series converges by direct comparison test. And you may be thinking to yourself, does that mean all of these converge? Not necessarily. So let's take a look at this last one. And the more you practice this, the easier it is to determine what you're going to pick to compare. But p-series and geometric are the most common, and those are usually pretty easy to spot. So this guy does look like a p-series because this looks like n to the 1/2, and this is really close to that. So we're going to notice that this starts at n equals 4, which feels kind of funny right here. But if I started at n equals 1, this would be the square root of 1 minus 1, which is dividing by 0. If I start at n equals 2, then it's fine, but I'm not going to get an integer down here. So that's why we start at n equals 4, just to help you out with that. So we're going to compare to 1 over n to the 1/2. That is a p-series function. P is equal to 1/2, which is less than 1. But if the power is less than 1, that means this series is diverging. So this series, our comparison series, if you will, diverges by p-series test. So if I were in a situation where I was comparing this to this, if this ended up being less than this, I could not confidently say that this is converging or diverging. Less than infinite may be infinite. It also may be finite. I don't know. I don't know what that is. So we need this to be bigger than this in order to be able to use the direct comparison test. So let's take a look. The question is this piece greater than or less than that piece as long as n is bigger than 4, right? Or 4 or bigger. So if I plug in a 4 here and a 4 here, well, this is going to end up being 1/2, and this is going to end up being 1. If I keep doing that because this denominator is always going to be less than that denominator, you could put in a 9, right? So the 1/3, this is going to be 1/2. This is always going to be bigger than that. So we're going to say greater than, and because this diverges for all n, right, then that means we're greater than for all n. Therefore, that original series diverges by direct comparison test. So I really like direct comparison. Most of the time we're using p-series and geometric series, which is kind of nice. I do want to write a note down here to make sure that everybody's on board. The whole idea behind direct comparison is smaller than finite must also be finite. This is an example of both converging. Larger than infinite must also be infinite. So that's an example of both diverging. Smaller than infinite maybe infinite, maybe finite. Larger than finite, maybe finite, maybe infinite. In situations where you try to use direct comparison test, but this is the result that you get, this is inconclusive. So let's zoom in a little bit. Inconclusive. You would have to do another test if you started down this track and ended up with one of these two situations. You would have to say, well, this test didn't work. I'm going to have to use another test in order to determine whether or not the series converges or diverges.